The conventional wisdom I've seen among founders is to pick an affordable model when they are building AI native apps and then write a ton of orchestration logic to help control how smart that affordable model is. This is exactly the wisdom we followed when we built our agent at River. We picked an affordable model, spent 3 months, spent engineering resources, spent our runway trying to make this agent sound smarter. And then at the end of that 3 months, we launched the product to our users. And on day one of launching that product, our users were using that agent in the most unexpected way, in the most nuanced way that we couldn't test. And that meant that the agent fell apart on day one. Now, to hotfix this problem and help us recover, what we did was strip out most of that orchestration logic and just switch to a smarter model. And immediately, our users started to stick around. Now, I want you to think about this for a moment. The alternative to switching to a smarter model would be to spend more engineering resources and more of our runway trying to make an affordable model fit into whatever use cases our users were trying to use it for. Which means that for the lifetime of this agent, we're going to spend some form of engineering resources trying to handhold that agent to complete its task. So when you think about being frugal, are you going to hire an AI engineer to handhold this agent and you still risk losing users because your AI agent isn't in quote smart? Or, and hear me out here, increase your token budget, retain your users, and then you can make a case to investors and partners that your product is actually sticky, make more money, and then offset that expenses. Now, once you've decided to go against the grain by picking a smarter but expensive model, my goal in the rest of this video is to walk you through how to stay frugal by maintaining a lean context. I'm sure you're probably familiar with what a context window is, but if you're not, it's just a container of all the messages or all the memory that an agent has about a conversation. It helps it understand where it's been in that conversation and then helps it decide where to go next from there. It contains the message the user sent, the assistant message, some tool call that the agent has to make to get the data it needs to respond to the user, the result from that tool call, and then more message to the user after it's made that tool call. In addition to all this, there is also the system prompt, which is a general instruction of how the agent should behave. But here is an often overlooked section of a context window, the tool definition. This is where we tell the agent its capabilities and how it should use the tools available to it to complete tasks. You can see in this example, it takes up 2K tokens, which is almost half of the context window. But here's where the problem starts to compound. If you think about how an agent works, it's basically an LLM constantly making two calls in a loop until it has all of the data it needs to then respond to a human. Now, that means that between the time you sent a user message and when you received the last assistant message, there's a chance that you've called your LLM multiple times, which means that you spent tokens for each of the steps that you needed to call that LLM. This reveals interesting problems on how your context grows. Let's take a look at a detailed example. This is a message turn, and the turn is simply the distance between your user message and the last assistant message. So in this case, we have a message is sent to the agent. The agent lets you know that it needs to make a tool call. It makes that tool call. The tool call returns a result. And then at this point, the agent can either respond or decide to make another tool call. And at this point in time, this context starts to grow again. The agent lets you know you need to make one more tool call, makes that tool call, produces the result, and then either responds or keeps going. But my point here is that at any given point in time, that the agent is receiving a message, what we're basically doing is injecting the entire context window back into that agent. And this is why it's easy for your context to immediately get out of hand. Now, let's say the agent has completed those steps and finally sends you the last message. You can see all the steps that it took to send that last message. What you can also do is send another message, which leads to a second turn. This time, we're not starting with a fresh context. We first of all inject everything that happened in turn one before we then send the user message and then get an assistant message back. The risk with this rapid growth, aside losing money on context token, is that you start exceeding 40% of your context window and start entering this zone where you risk hallucination before the user even achieves their goal. And what my team did when we found ourselves in this situation while using the affordable model was to try to force the agent to use a particular tool to classify its intent. When it classifies its intent, then we can control its trajectory. But the problem with trying to control its trajectory is if the agent wrongly or misclassified what the trajectory should be and tries to recover, it doesn't have access to the tools to recover from that. And then it leads to the agent completely hallucinating how we should perform the task that was given by a user. And the way we solved this was to use progressive disclosure. But for this to be successful, we actually had to use a smart model that was good at knowing what to disclose to itself. Here's what it looks like in practice. The only thing we had in the system prompt was the agent's identity, the user's context, and instructions to the agent letting it know that it has more capabilities, even though it doesn't seem like it does. It does, and the way it can find those capabilities is to use the load skill tool to fetch more information about its capabilities and then figure out how to solve the problem. Now, when it does, it realizes that it's capable of creating and managing users' tasks and that it can use the search tool to fetch all the tools relevant to help it create tasks, manage tasks, list tasks, fetch tasks, whatever the case may be. So tool search returns a set of tools that are relevant when you're using a task skill. Now, in this hypothetical example, doing this reduced our context window from 6.5k tokens to 4.5k tokens, but we did not stop there. We went a step further, and that step further was to look at the actual data that the two results we are fetching were returning. If you look at this example, raw data, we're getting data from our database, a JSON data that contains information about the task, the ID, the title, the status, and the priority. And this is about 212 tokens. And this is that same data represented differently. We have the task ID, we still have the title, we have the status, and we have the priority, and it's just 64k tokens. This is almost half the token when compared to what we were getting from the raw JSON data. Now, this led us asking ourselves the question, how do we give the agent access to all the data it needs without data loss, but without all of the noise that comes with the raw JSON data? So what we did was hide an agent inside a tool call. So when the main agent makes a tool call, we don't actually fetch data directly and give it to the agent. A sub-agent handles fetching that data, which means that that sub-agent can focus on thinking through that data, cleaning the data up and simplifying it, so the main agent just receives the clean data. When you compare that where we're coming from, we originally had 6.5k tokens in our context window, and we've successfully halved that number to 3k tokens. Perfect. Now you can see that even though you've increased your model budget, you can still save on your token budget. I'm going to show you some code examples on what we did to actually get this working. We used the generate text function from the AI SDK to abstract the agent loop. And then we choose our smart model to be the Sonnet model. Now for the system prompt, what we're doing specifically is make sure that we just provide a brief summary of what this agent can do, the user's context, and then finally a summary of the available skill, not the entire skills, just summary. So if we jump into what build skill summary does, you can see that we just include the skill name and the skill description. Another important thing we're doing here is that we make sure that the only active tools for this agent at first is the load scale tool and the search tools. Now, this means that in as much as the agent can see that it's capable of a few things based on what it sees in the skill name and descriptions, it can't use those tools and skills unless it loads them by calling these tools first. The prepare step function helps us control what happens at every single iteration of the agent loop. But here's what's important. We are not forcing the agent into any trajectory using classify intent. Instead, what we're saying is choose whatever you want to do. When you do, let us know and we'll give you the skill and the tools you need to complete those tasks. And why this is important is if the agent decides, oh, I know I chose this previous direction, but when I read this message that the user sent once more, I've realized that instead of creating a task, I actually need to create an event. If that's the case, the agent can step back, find the scale for creating events, let us know that that's what you want to do. And then we can clean up the scale for creating tasks and the tools for creating tasks from its context, and then give it the skill for creating events and the skill and the tools for creating events. So in practice, what we're doing in each of these steps is called the select step state function. And this function basically finds the latest skill that this agent called and the latest search tool that it called. And then we pull out the skill name and those skills and return it from this function. Now with that skill name, we can build a new system prompt. This time, we inject the base system prompt as usual. But in addition to that, we also attach the full skills instructions. Now, once you have this new system prompt that contains the skill for this action that the agent needs to complete, alongside the tools that it needs to complete those actions. We then let the agent know that these are the only thing it needs to focus on. It only needs access to the active tools to complete this task. It needs just that skill and the base system prompt. And then finally, we clean up the messages to remove all of the meta tools, which includes the load skill tool and the search tools tool from the message history and from the tools description. Now, to show you how this keeps your context clean, I'm going to jump into my terminal and run run chat. I'm going to choose a few scenarios to seed the database. Let's pick positive for the energy and deadline pressure for task scenario. When I say hi, agent is going to respond with a response. It's going to just let me know what it's capable of. But what I want you to pay attention is that for this turn, it spent 1,000 token for everything. Now, when I say what's on my schedule, it's going to load the skill for fetching tasks. It's going to use the tool fetch tool to find the tools it's going to use to load those tasks or fetch those tasks. And then it realizes that there's a tool called task list, which is also a sub agent I can use to fetch these tasks. Then fetches those tasks and then breaks them down for me. Now, why this is important is when I say thanks and hit enter, you would see that this turn is going to get immediately cheaper because we are not using all of the information that was required in previous turn in this turn. We've stripped out all of that skill and all of that tool that we had in this turn, and we've gone back to the base system prompt without any of those tool descriptions and the skills. But of course, we still have our message history, which is why it's now 1,489K tokens instead of 1,000K tokens from the first time I said hi. And also the tool result when we fetched the task list is also available in our context, which means we can keep chatting with this agent without the agent losing any data of what has happened in this conversation, but then it stays focused without all the noise of a meta instructions that it doesn't need to complete this given task. Now, with that said, that brings us to the end of this video, and I hope it helps you build smarter agents and smarter products. And I hope I see you in the next video. Bye.